All right, Chemistry 3101. We're continuing on with synthesis today, chapter 11, and I wanted to start off by taking a look at some synthesis problems. These are problems that are pretty much ubiquitous in organic chemistry. You see Avogadro's number of questions like this, where you're given a small molecule and then you're asked to make something from it. Well, there's a couple of things that I would do to start out with a problem like this. The first thing I would do is say, well, I'm starting out with 2 carbons in my molecule and I'm ending up with 4 carbons in my molecule. Now, we don't have any way to increase the size of the carbon skeleton except for using sodium amide to do a deprotonation and then adding an electrophile. Now, in this case, we would use ethyl iodide because we need to add 2 more carbons. But before I write that out, I want to think about retrosynthesis, right? Retrosynthesis is going backwards. You start with the product and you think, well, how would I make this product, And what we have here is a halohydrogen, right? We have a hydroxyl and a bromine on adjacent carbons. And the only way that we know how to make a halohydrogen would be to start with this alkene, would be to start with 1-butene. And then if we treated that with bromine, it forms a bromonium ion. And then if we put that in water, water comes in and acts as a nucleophile. It is going to do the nucleophilic attack at the more substituted carbon in order to produce the halohydrogen. Then what that does is it simplifies the question a little bit, because now we're just thinking, okay, well, how do I get from acetylene to 1-butene? All right, and the strategy that we're going to take is, like I said, we're going to start by adding a couple of carbons. And again, you've only got one reaction in your synthetic toolbox, if you will, right? You've got adding sodium amide to make the acetylide ion, and then the second step, you'd add ethyl iodide. If you wanted to write it out like that, that works. Or if you want to write ETI to abbreviate the ethyl group, there's nothing wrong with that either. And what that's going to give you is that's going to give you 1-butyne, right? This is 1-butyne. And then if we want to reduce the 1-butyne to 1-butene, well, we got 2 possibilities, right? Because if we have a terminal alkene, it is not cis, it is not trans. Therefore, we can use the cis reduction using hydrogen and Lindlar's catalyst, or we could use our conditions for trans reduction, which is sodium metal and liquid ammonia. Either way is totally fine with this guy. However, scientists usually prefer hydrogenation because they don't have to work with sodium metal. And you're thinking, well, hydrogen is kind of dangerous too. Yeah, it is, but it's a lot simpler to work with than sodium metal. So we'll use H2 and Lindlar's catalysts. There we go. We end up with 1-butene like that. And then in our last step, we're going to treat that with bromine in water. And there you go. We have a total of 1, 2, 3, 4 steps to complete the synthesis. So again, these are the kind of strategies that you want to take. Let's take a look at another one. Let's take a look at 11.9e. And again, I encourage you not to look at the solutions manual, which everybody has access to. But if we start out with 2,3-dimethyl butanes, that's this compound here. And then it's kind of interesting problem. We want to add a hydroxyl on one of these carbons, right? We have this primary alcohol that we want to make. How are we going to do that? Well, you can see that there's no change in the carbon skeleton, right? I'm starting out with 6 carbons and I'm ending up with 6 carbons, so nothing to worry about there. However, something that everybody should be aware of is that whenever we start with just an alkane, you literally have one reaction at your disposal, right? The only possible reaction that we've learned with an alkane is to take it and treat it with bromine and light, and that is going to be selective in terms of its regioselectivity and brominate at the most substituted carbon, at the tertiary, at one of the tertiary carbons, right? If you were to treat that with chlorine, you'd end up chlorinating here and here, right? You'd get chlorines all over the place. But we just want to use our bromine so that we get one regioisomer. Okay, well, that gets us with a bromine in on this tertiary carbon, which is really great. But if you got stuck at this point, if you're thinking, I'm not sure where to go next, another thing you could do would be to think about retrosynthesis. If we take a look at this primary alcohol, well, we don't have many ways to make a primary alcohol, but we would have to make that primary alcohol by an anti-Markovnikov addition to this alkene, right? If we had this alkene, we could treat that with borane in THF, and then in the second step, we could treat it with sodium hydroxide and hydrogen peroxide, right? We can definitely do that. Well, then the question gets a little simpler because now we're thinking, okay, well, how do I get from here to here, right? How do I get from this tertiary bromide to this alkene? And you can see that we need to do an E2 reaction. And to do this E2 reaction, right, we have two types of beta protons. We have these ones, or the type that I'm highlighting in blue here, and then we also have this one here that I'm highlighting in green. If we want to selectively abstract the one that's in blue, we're going to use a non-hindered base, right? It's going to produce the less substituted alkene, therefore the less stable alkene. However, if you use that big bulky base like potassium T-butoxide, and I'll just draw it out like this. So this is potassium T-butoxide. That's going to preferentially pull off this proton to produce the double bond loss of leaving group. It's an E2 mechanism, and then you end up with the desired alkene like that. All right, then you just got a couple steps left. The anti-Markovnikov addition of water, excuse me, across a double bond. First step, borane and THF, followed by hydrogen peroxide and sodium hydroxide. All right, there we go. So sometimes I like to draw mechanisms along the way that can be very helpful in providing a rationale for the synthesis. Excuse me. Let's try another one. Let's try one that's a little longer. Let's try H. So if we take a look at, this is question 11.9H, we're going to go from this alkane. So this is 2-methylbutane, and we want to make this compound there, which would be 3-methyl-1-butyne. So if you look at the number of carbons, we have 5 carbons over here. Then we have 1, 2, 3, 4, 5 carbons over here. No change in the carbon skeleton. Now, in terms of what we can do with the starting material, I'm going to go a little faster now. We really only got one option. That is to brominate. So we treat it with bromine and light. And we're going to end up with this guy right here. Well, that doesn't look anything like my final product, does it? So again, this is where retrosynthesis could come in very handy, right? If we were to think backwards, we could say, well, to make that terminal alkyne, since we're not adding carbons, right? We can make a terminal alkyne from a primary alkyl halide and use acetylide, but that would cause an increase in the number of carbons in the carbon skeleton, so that's not useful to us. And so really, we've got one option here. The only option that you have is to make this compound, right? If you have this vicinal dibromide, all you'd have to do is treat this with excess sodium amide in the first step, and then treat it with water in the second step. Now the question is still not easy, but it gets maybe a little simpler because now we just have to get from here to here. Well, I haven't done this with you yet, but sometimes it's nice to take 2 steps backwards, okay? We've done one retrosynthetic step, but let me just do one more. Because if we have this vicinal dibromide as the precursor to the final product, there's only one way that we know how to make that vicinal dibromide, and that would be to have this alkene. Right? If we have that alkene, all we have to do is treat that with bromine, right? And we would end up with the vicinal dibromide. Now, hopefully, the question becomes much clearer. I want to get from here to here. So what am I going to have to do? There's no beta proton that I can eliminate in this molecule that's going to give me the alkene that I want. But if I could move the bromine over to this position, then I could do an elimination with potassium T-butoxide to produce this terminal alkene. Well, let's move the bromine, and we talked about how to move the bromine around the molecule. First, we're going to treat it with sodium ethoxide. So let's draw that over here. So this is sodium ethoxide, right? That's going to eliminate this beta proton, so the ethoxide, I'll draw a quick version of the mechanism, is going to eliminate that proton, produce the double bond, but we end up with this alkene. Now, what if we were to do an anti-Markovnikov addition of HBr across this? Just give me 1 second here and I'll write it out. Then we're going to end up with this molecule. And hopefully once you get to this point, the question should maybe, come more into focus, if you will, at this point, right? Because hopefully you can see that we can get from here to here with relative ease. All we have to do is treat this with a hindered base like potassium T-butoxide, and that's going to produce the desired alkene. Then we brominate it, and then in the last step, we treat it with, and I'll write it out here in black so you can see it a little clearer, with sodium amide, and then with water in the last step. So how many steps do we have total here? It's quite a few. We have a total of 1, 2, 3, 4, 5, 6, 7. So this is a 7-step synthesis. Not trivial, is it? 7-step synthesis. Well, let's take a look at another one. And this time I'm going to pause a little bit and I want you to think about the problem. And I want to ask you, how would I go from this molecule? What if I had this primary alkyl bromide? So this is 1-bromobutane, and I want to make this compound. I want you to think really hard about this. Again, it's not a trivial problem. If it was easy, anybody off the street could do it. But I want you to think about this problem for a second. I want somebody to give me a proposal about where they might start with a problem like this. Could anybody tell me anything about where they might start with a problem like this? Good problem, and not a simple problem. The first thing you might want to ask yourself here is there a change in the carbon skeleton? Does it have anything to do with mercury? I'm not sure if I would need to use mercury here. Is there a change in the carbon skeleton? Is the carbon skeleton changing in some way? Yeah, so somebody's saying ethyl iodide. I'm not sure about ethyl iodide, but we're in the right vein in that somebody is saying that we need to add 2 carbons, and they're absolutely correct, right? In this molecule, we have 4 carbons, and in this molecule, we have 6 carbons. Okay. Add 2 carbons. Yeah, we need to add 2 carbons to the molecule. Now, does anybody remember what this is called here? This is called an epoxide. Epoxide. Now, that might have thrown you for a loop saying, well, Mr. Dion, you never talked about epoxides. Yes, I did, okay? So this is where epoxides would have come up in this class. Let me show you. When we took an alkene, okay, let's say we took an alkene like this, and we treated it with MCPBA, followed by H3O plus, we did the anti-dihydroxylation, right, of the double bond. So you'd end up with 2 hydroxyls like this plus the enantiomer. Well, the intermediate that's formed after the first step, right, the intermediate that you get would look like this, where you would have an epoxide like this. Now, both of the bonds would be on the same face of the molecule, so I'll just put them down like this, okay? Oops. But that is what an epoxide is, okay? This is an epoxide. So that's the only time that we looked at making a 3-membered ring, and then you would treat that with H3O plus in the end, right? And then you end up protonating this, and then water comes in and acts as a nucleophile, like this, and then you pop the ring open. So in order for us to make that 3-membered ring, the epoxide, we can say, well, I'd have to have 1, 2, 3, 4, 5, 6. I'd have to have this alkene, and then I could just treat it with MCPBA to do the what's called an epoxidation to make the 3-membered ring. Now, hopefully, the question becomes a little more reasonable. How do I get from this primary alkyl halide to this alkene? We need to add 2 carbons to the molecule, right? We need to add 2 carbons, so let's treat it with sodium acetylide. Sodium acetylide. Here we go. That's going to do an SN2 reaction, right? Because this is a primary alkyl halide. That's going to give us, oops. That's going to give us this molecule. 1, 2, 3, 4, 5, 6 carbons. And now all we have to do is reduce the alkyne to an alkene. For that, we would use hydrogen and Lindlar's catalyst. And then in the last step, we're going to treat it with MCPBA, or you could put RCO3H. Either one is going to work to make that epoxide. So this is a perfect example of why we have to understand mechanisms and have a rationale, or understanding of mechanisms would be crucial to solving this problem, right? And knowing the intermediate. Now, in chemistry 3111, we do a whole chapter on epoxides, pretty much. I mean, we deal with alcohols and epoxides in the same chapter, but we spend an entire day or more just talking about epoxide chemistry, which is pretty interesting. And the 3-membered ring is strained, highly strained, so not always that easy to make. I worked with a woman in graduate school who was trying to make a cyclopropane, and she worked on it for, I don't know, half a year or something, just one reaction. So, yeah. Anyhow, let's take a look at one more, and then we'll talk about some green chemistry for a second. Let's try this one. What if we had something like this? This would be a perfectly legitimate question. Very good question for your next quiz on Monday. So we have this geminal dibromide, and we want to make this guy. We want to make a ketone like that. Is there any change in the carbon skeleton here? Yes or no? Is there any change in the carbon skeleton here? No. Thanks, Stephanie. Thanks, Megan. Absolutely. There's no change at all, right? We're starting it with what? 7 carbons to start, and we end up with 7 carbons at the end. Well, again, if you know your reactions frontwards and backwards, and if you could say to yourself, well, I don't have many ways to make a methyl ketone, do I? Right? I don't have many ways to make a ketone at all. I mean, we could make a ketone through ozonolysis, but that would mean we'd have to start with a molecule with more carbons, right? Because ozonolysis cleaves a double bond and you end up with 2 molecules. And so the only really option that you've got in terms of, starting materials would be to start with the alkyne, right? If we had this terminal alkyne, all we have to do is a Markov-Nikov addition of water across that, which is going to form the enol, which will tautomerize to give us the methyl ketone. So hopefully now it becomes much simpler, and I don't like to say simple in chemistry class, but hopefully by now you know how to take a geminal dibromide and convert it into that terminal alkyne. What are we going to do? Same old conditions every time, right? We treat it with excess sodium amide. That's going to do the double E2. You end up deprotonating with one of the excess equivalents to make the alkanide, and then you have to throw in some water, which affects the protonation, and that is going to give you this compound, that alkyne that I have drawn in blue. I'm just redrawing that same compound. So now, if we do the Markov-Nikov addition of water across that triple bond, it should produce the enol, which will tautomerize to give us the ketone. Could anybody tell me what the conditions are for the Markov-Nikov addition of water across the triple bond? What would the conditions be? Does anybody have an idea what you would use for Markov-Nikov addition? We can't just use sulfuric acid. It doesn't work. Yeah, thanks, Patrick. Absolutely. Good. Good. Right. So Patrick has it. He's 100% right. But I just want to point out something. If you were to say, well, if I just want to do an anti-Markov-Nikov addition of water, I'll just use H3O+. It's been tried, okay? But trust me, people have tried it before, long before I was around. And the thing is, it probably does work to some extent. Okay, it probably does to just take it and throw it in acid. Yeah, it probably does. But the problem with it is that it's a very slow reaction, very sluggish. So, you guys studied reaction rates in general chemistry too, and we don't appreciate reactions that are too slow. And so the reason behind the whole mercuric sulfate thing is that speeds up the reaction. It spiffs it up, if you will. It's not the right word to use, but it just increases the reaction rate and makes this a useful reaction. I told you I would never ask you the mechanism of this reaction, although the book does go into a little bit of detail about it. But then you're going to end up producing this enol, right? Here's our enol. And that enol is going to undergo tautomerization in acid to produce the methyl ketone, right? This is a methyl ketone. All right. It's a cool reaction that we'll look at in organic chemistry too with methyl ketones called the iodoform reaction. Something to look forward to there. Well, I'm sure you're not tired yet, so let's try one more. I'm just looking at some problems that I have here. I think this is another real good one. What if we wanted to do something like this? It's an interesting reaction because you're ending up making acetone in the end. This is acetone, which is nail polish remover. Also can be used to clean glassware. If you're in the chemistry 3102 lab, we use it to clean glassware a little bit in that lab. We don't like to waste it because it's bad for the environment. But anyhow, if we start it with 2,3-dimethyl butane and we want to make acetone from it, I don't know why you would want to do this, but it's more of an exercise, right? Some syntheses today even are just done by researchers just for the heck of it. And if you're like, what, just for the heck? Yeah, just to push the boundaries of synthesis, to develop and discover new reactions. I worked on a synthesis like that. Well, I guess I consider it a synthesis like that. But anyhow, that's another story. All right, so could anybody tell me what my first reaction is going to be? What's my option for a first reaction here? And it's not a trick question. I don't like trick questions. Yeah, thanks, Josh. Absolutely. I'm going to take this and I'm going to treat it with bromine and light. That's all I got. There's a thing called the organic chemist toolbox, right? You have so many tools, and this is one of your tools that you've got in your toolbox. So if you brominate here, well, it might be kind of funny to think about, why you would make acetone, but let's take a look at the carbon skeleton. Here we have 6 carbons, and here we have 3 carbons. I'm just going to throw this out there to my students because I don't have a better way to ask it, but can anybody tell me what would be a good last step for this reaction? How do you think about, acetone retrosynthetically? Where would that come from? We don't have many ways to make ketones. Yeah, thanks, Josh. Absolutely. So the last step is going to be an ozonolysis. If you were to have this alkene and you were to treat this with ozone followed by DMS, that's going to give you're going to start out with 1 mole of this, and you're going to end up with 2 moles of acetone. But whatever, you double your product yield. Nothing wrong with that, right? Absolutely. So make sure that the second step is to use DMS. H2O is used for the ozonolysis of an alkyne. So this is an alkene. So second step is either dimethyl sulfide or zinc and water. There we go. So what are we going to do? We're going to take this. We're going to treat it with sodium ethoxide. We're going to deprotonate. We're going to make the alkene. So this is 2,3-dimethyl 2-butene. And then we take that and we treat it with ozone, followed by DMS. There you go. Kind of an interesting reaction. We don't look at a lot of reactions in this class where you start it with 1 mole, and end up with 2 moles of something in the end, but kind of cool. Very interesting chemistry there. All right, well, let's get back to the lecture slides. And I told you I want to talk to you a little bit about green chemistry. So the questions that we just looked at all came from question 11.9, which is really good practice for your, knowing your reactions frontwards and backwards, being able to look at a reaction and say, or sorry, a transformation, if you will, and say, well, what would I have to do in order to effectively perform this transformation in the lab, right? That's the whole point. Well, the section about green chemistry, now I said we're going to skip it. I don't know if I would ask you a lot about this. I think this summer when I teach this class, I'm going to leave out the skipping part. I'm just going to say we're going to talk about it because it's really short. If you go to section 11.6 in your book, like I said, you can read it in under 3 minutes. It's not long at all. I'm sure all of you are very fast readers. So green chemistry is something that's kind of new, ever since society decided to become a little more environmentally conscious, and we could, sit here and debate when that happened. But I'd say in terms of chemistry, which is something that I'm familiar with, I'd say the whole concept of, trying to do reactions that are more environmentally friendly has really come to the forefront, let's say in the last 20 years, okay, since the year 2000-ish. So green chemistry is governed by 4 guiding principles, right? Well, you've all done things in the lab. You've all done reactions in the lab. At least I think most of you have. Most of you are in chemistry 3102. Now, when you get into organic chemistry too, in that lab, you do a lot more synthesis reactions where you start with a starting material and you end up making some kind of product in the end. And what you'll see is that instead of having one waste bottle, like we usually do in organic chemistry 1 lab, sometimes we'll have 2 and maybe even 3 waste bottles. Okay, so you think about all the labs that you've done, there's usually a waste bottle involved, almost always. So where does that waste go? Well, that waste is going to go into the environment, or sometimes it can get incinerated or whatever. But the whole concept is that we want to prevent waste, right? We're trying to limit what goes into a landfill and what goes into the environment. And what else can we do? We can use less hazardous substances, right? If you think about just using aqueous acid, that is not highly toxic, right? If you think about just dilute aqueous acid, I don't think about that as being toxic. But what if you use something like mercuric sulfate, right? That's got mercury in it. Mercury is bad for the environment. So if we can, avoid using heavy metals like mercury or osmium, right? Think about osmium tetroxide. Osmium is highly toxic. If we can avoid these kind of reagents, we will do it. Something that doesn't even come up enough in this class, I find, is solvents, right? Dr. Klein, and it's not just him, most organic chemistry 1 textbooks don't say enough about solvents. We talk about them a little bit. But all of these reactions that we look at, every reaction has to have some kind of solvent in order to provide an environment where the molecules can collide with one another. Well, there's lots of environmentally unfriendly solvents that are used by organic chemists. Things like dichloromethane, CH2Cl2. It's got chlorine. It's bad for the environment. Another one would be chloroform. One that our book doesn't even mention. It doesn't even mention CCl4. That's carbon tetrachloride. Now, that used to be a popular solvent with organic chemists. You look at literature from the 1970s and probably even into the 1980s, you see carbon tet everywhere. People are always using carbon tetrachloride. In fact, I worked with a gentleman who told me, when I was a graduate student, we washed our hands with carbon tetrachloride. This is really bad for the environment, and it's also dangerous to wash your hands with that. And I won't go into the whole details about that, but we want to avoid chlorinated solvents. What if we could do every reaction in organic chemistry just in good old water? That would be great. It would be great. It's not reality, but we want to try to avoid using harmful solvents when we can. And the last one is something that was developed by a scientist named Barry Trost. So Barry, if you want to Google him, I'm 99.9% sure there would be a Wikipedia entry about Barry Trost because he's a very famous organic chemist. I've seen him speak a couple of times. Anyhow, is the concept of atom economy, is that we want to use reactions where just about everything that we have in our reagents, all the atoms in those reagents are incorporated into the products. And if you're wondering, what do you mean by atom economy? Let me show you here. Let's say you want to do a Markovnikov addition of water across this molecule. So the same molecule both places here. So this is what? 2-methyl-2-butene. Okay, well, you've got a couple of options, right? You could use a catalytic amount of acid and water. Well, look what happens is that the water molecule, right, the whole dang water molecule is incorporated into the final product. The only thing that doesn't get used or isn't in the final product is the catalytic amount of acid. But that's catalytic. I mean, you don't even need a 1-to-1 molar ratio. So there's almost no waste in the acid catalyzed hydration of this alkene. However, what if you do oxymercuration, demercuration? All of the atoms that are highlighted in red here, none of those get incorporated into the final product, okay? The water that gets added to the molecule comes from this water molecule, and the hydrogen comes from the borohydride. So everything else here is waste, right? All that mercury, the boron, salts that are produced, all that junk goes in the waste. So that's what we call a poor atom economy. Now, if you want to Google atom economy, you can see that there's an actual formula that you can use to calculate atom economy as a percentage. I'm not going to go into that, but hopefully you get the idea that some reactions are a lot nastier for the environment than others. And if you're thinking, well, come on, Mr. Dion, if I'm in the lab and I'm just doing, come on, I just want to do this on, 30 milligrams, really? Is it that big a deal? Well, what if this reaction is used to make a prescription drug that is used by millions of people? Well, then, you're dealing with a lot more waste, right? So these are serious considerations, things we really have to take into consideration. What are other things that we could do to improve the environmental friendliness of the chemistry that we're doing? We could use catalysts, right? Like that catalytic amount of hydrogen or a catalytic amount of a metal. Something else I'll tell you that's really cool about catalytic hydrogenation. So you know how we talk about hydrogenation using palladium, platinum, or nickel? So a lot of those hydrogenations can simply be done using, and I'm not kidding, and I know I told you this, just using a party balloon. So you put hydrogen in here, and then in your reaction mixture that's stirring, you'll have your solvent, but you'll have, let's say, palladium. Okay, let's say you're doing a hydrogenation of some alkene. I don't know, we can pick, let's say we're hydrogenating, trans 2-butene and we're making butane. I don't know why you do that, but let's just imagine we're doing that. So here's something really cool that I learned when I was a graduate student is there were some guys working in a lab upstairs from me, and they were working on attempting the synthesis of Buckminster fullerene, which is C60. Anyhow, they were doing a lot of catalytic, not just hydrogenations, but other kind of organic reactions that required catalysis. So it required small amounts of these expensive metals. And what they found is if they took the glassware after the reaction was done and they cleaned everything up, okay, what they found is that the palladium or the precious metal would actually get stuck to the inside of the flask. And so if they didn't wash the glassware, if they just left it dirty, they could start the next reaction and the catalyst would be active enough, or there'd be enough of it that it would actually end up back in the reaction mixture. And so that's how little they needed. They just literally took the residue of the metal that was left on the glassware. They were able to do a catalytic reaction. So that's kind of cool. Other things that I don't think about nearly as much would be energy efficiency, right? When you turn up a hot plate, what are you doing? You're wasting electricity, or you're consuming electricity, I should say. So if you can do a reaction at room temperature, hey, or that's going to be more efficient than one that's going to require you to heat it all up. And then the last one is renewable feedstocks, using starting materials that come from grains or corn as a source of carbon instead of molecules that come from crude oil, that come from the petroleum industry or the refinement of crude oil. So all important things to take into consideration. And I think that green chemistry is something that students need to be introduced to in 2021. Well, let's talk about the last section. So increasing proficiency. This is the kind of thing that I could sit here and yammer on to you about for the next 25 minutes, but you probably wouldn't want to hear me do that. So, what's the bottom line, you guys? I mean, I've taught this class long enough to know that you just have to know the reactions. There's nothing more than that. Now, if you're angry at organic chemistry because it's a lot of memorization, I still don't think it's as much memorization as classes like anatomy and physiology, right? Those are pretty tough. Look, and just the bottom line is, there are some reactions that you have to memorize. Okay, Mr. Dion's I'm not going to lie to you. That's just a fact. Okay. There's even some reactions that I've just memorized. I'm not sure what the mechanism is. I might be able to make something up, but you've heard me say this 100 times, and I'm going to repeat it more and more to you. And that is, the greater understanding that you have of a mechanism, the easier synthesis becomes, right? Because you really understand how things function in the reactions that you use. Now, if you get frustrated by mechanisms, again, they're not easy, right? They're not easy. Some of them are easier than others. But what you might want to do is every time you see a reaction, you're like, what's that mechanism? Just maybe bookmark it or something on your computer and just say, hey, well, let me take a quick peek at, oh yeah, now I remember, and that will help you memorize those mechanisms. As far as creating your own synthesis problems, that's up to you. If you want to do that with a friend, invent some synthesis problems, it's a fun thing to do. I don't do it with my students, but it could be a good way to get some more practice in there. Anyhow, here's just an example of them coming up with a practice problem. And then the last thing I'll say about this chapter is that as you progress in organic chemistry, you're going to find you're going to run into more and more synthesis problems where there's going to be more than one answer. Right? Let's say we wanted to take this molecule. So what is this? It would be cyclopentyl We want to take this molecule and we want to make a primary alcohol. Well, the first thing that I would think would be hydroboration oxidation, right? What's on the top line here. But why couldn't you do an anti-Markovnikov addition using HBr and peroxides to make the primary alkyl halide, and then hydroxide can come in as a nucleophile in the second step and do an SN2? Why won't that work? Nothing wrong with that. Okay. In fact, both of these are good ways of doing this transformation. All right. So there you go. That covers all of chapter 11. Well, with that in mind, I want to take a look at some more questions. And I want to go over question 11.11 and 11.12. Now, again, I've taught the class long enough to know that by this point, and I'm saying this, just as somebody who's got experience teaching this class, that usually by this point in the class, I'll have a range of, what's the word I'm looking for? Confidence or proficiency, maybe, of all the reactions that we look at. Some people will know them frontwards and backwards, right? You're like, I have them all down pat. I know them all. If you do, awesome. That is awesome. Okay, I'm super happy. It makes me really juiced. Okay. However, I'm sure there's some people that are still struggling. What is this reaction? What is that reaction? Still trying to get it sorted out. So the next couple of questions I want to look at, we're going to actually tone it back a little bit and just go really slowly through a bunch of different one-step synthesis. So which is, again, a politically correct way of saying just plain old reaction. So this is question 11.11. Again, if you're the kind of student who's still struggling, trying to get all of the reactions down pat, you're thinking, well, I got some of them I don't. Don't look at the solutions, okay? That's not going to help. Sometimes you just have to bang your head against the wall, maybe. Don't do that, okay? Don't say that. Mr. Dion told me to, hit my head against the wall. But anyhow, if I want to take this alkene and I want to make an alkane, now I know that a lot of my students have the answer right away. Can anybody tell me what would be the best way to take an alkene and make an alkane? And it's not a trick. It's talking about some good old reactions that we know. If I wanted to do this type of transformation, what would I do?
That H2 and platinum.
Absolutely, 100%. Okay, perfect. So again, it could be palladium, platinum, or nickel. Chris says hydrogenation. You're both 100% correct, right? It's always good to know the name of a reaction. And what you'll see in organic chemistry too is that you'll learn a lot of reactions that are named after scientists, like Birch reduction, or the Grignard reaction, or the Chichi-Babin reaction, or the Voller reaction. Anyhow, you learn all kinds of reactions that are named after different scientists. The Wittig reaction is a big one. Anyhow, let's see. What if we wanted to do an anti-Markovnikov addition of bromine across that double bond? Well, in that case, we would use hydrogen bromide and peroxides, right? That's the anti-Markovnikov addition of bromine across that double bond. What if we want to do a dihydroxylation? If we want to make this molecule where we have a hydroxyl group here and we have another hydroxyl group here. Well, there's many ways that we could do this. Now, this one isn't syn or anti-addition is neither here nor there because this is not a stereocenter. And so you could select a variety of ways. You could use first step MCPBA, second step acid, or you could use one of my favorites, a catalytic amount of osmium tetroxide followed by N-methylmorpholine N-oxide, NMO. That works too. What if you want to make a halohydrin? Okay, if you want to make a halohydrin, what would the conditions be for the synthesis of a halohydrin? Can anybody tell me what I would use then? It's a halohydrin. Let's see, Patrick, what'd you put? Absolutely, you're 100% correct. So Patrick says, put some bromine on it, right? So react it with bromine and put it in water as a solvent. Okay, well, I'll do the next one a little quicker because this is a reaction that we've looked at quite a bit to do a dibromination. Now, again, here, now it is an anti-addition, but that's neither here nor there because this is not a stereocenter. But that you use bromine. Now, if you're the kind of person who's like, why is this, this is the halohydrin because it's in water, but what's the solvent here? The book brings up solvent once in a while, but this is a reaction where you would use something like dichloromethane, that nasty chlorinated solvent that we just talked about. Let's see, let's keep on moving here. What if we want to do an anti-Markovnikov addition of water across the double bond? Well, I feel like we've talked about this a lot. Borane and THF followed by H2O2, hydrogen peroxide, and sodium hydroxide. Now, look, this is the type of mechanism that we looked at. Okay, now I probably won't ask you questions specifically about that mechanism, but this would be a perfect example of a mechanism that is within your grasp. Okay, it's totally, understandable. And I did explain why you get anti-Markovnikov addition based on the addition of the borane. But if you understood this mechanism, that would be the keys to the kingdom, man. That will tell you everything you need to know about anti-Markovnikov addition of water. What if we just want to do, if we just want to do a straight old Markovnikov addition of water across that double bond? Well, we're not going to end up with a carbocation rearrangement in this case, so we would just use hydronium. There's a couple other reactions in this problem, isn't there? What if we want to take this, the 2,3-dimethyl butane, and we want to brominate it? For that, we would just use bromine and light because that's a radical mechanism. And then the last one, I don't really have a lot of room here, but if we want to take this and do an elimination and make the Zaitsev alkene, right? Because that's what is in the middle of the slide. This is the Zaitsev. For that, you would use potassium T-butoxide, like that. Okay, there you go. So that deals with a lot of the alkene chemistry. So alkene reactions, and there's a lot of them that we learned. Let's take a quick peek at some alkyne reactions. So let's see, if we start with this intermediate, so we have a triple bond here, so we have an alkyne. All kinds of different reactions here. I'm going to try to do this as neatly as possible. I know I'm going to botch it, but whatever. If I want to take this guy and I just want to do a Markovnikov addition of one molecule of HBr across the bond, or across the triple bond. I'm just going to write this guy here in the meantime. Okay. If I want to do this first step here to just add one molecule of HBr across the double bond, the way I would write that down is I would say HBr, right? It's a Markovnikov addition, but I would specify one molecule, one equivalent. One equivalent means if you have 10 moles, you're going to add 10 moles of HBr. If you had 2 moles, you're going to add 2 moles of HBr, right? That's what one equivalent means. It just means a stoichiometric ratio of 1 to 1. Right, if you want to add another molecule of HBr across that double bond, what are you going to say? Now you can just write HBr. Right, you don't have to be as specific about the one equivalent because even if you had excess, nothing else is going to happen. So you can just write HBr. If we want to take that geminal dibromide and convert it into the alkyne, in the first step, we're going to use excess sodium amide. In the second step, we're going to use water. It's a reaction that we've used a lot. What else? If we wanted to go from the triple bond to the geminal dibromide, here it would be like a double Markovnikov addition. So you would just put excess hydrogen bromide like that. Okay. What if we want to make the vicinal dibromide? If we want to make this compound, So you need to know the difference between geminal and vicinal, of course. This being the vicinal dibromide. How would I go from here to here? Well, sorry, it's going from here to here. To do that, you would do the double elimination. So first step is sodium amide, followed by water. Again, you need to know how to draw that mechanism, the double E2, followed by the deprotonation. Let's take a look at a reaction where we increase the size of the carbon skeleton. If we want to add a methyl group, right? If we want to tack a methyl group onto the end, okay, this is probably this is, in fact, the only way that we have to increase the size of the carbon skeleton is to first treat it with sodium amide. Sodium amide, which does the deprotonation of the terminal proton, right, because it's got a pK of 25. And then we can alkylate that using methyl iodide as an electrophile. We've increased the size of the carbon skeleton. Let's see, what else do we have here? What if we want to make cyclohexane carboxylic acid? So that's this molecule. If we want to do that, I think you all recognize that that's just an ozonolysis reaction, right? Cleavage of that triple bond, because we have one less carbon in this molecule than we do in the starting material. The first step is ozone, but the second step is not DMS. The second step is H2O when we have an alkyne. And not only will we end up with cyclohexane carboxylic acid, this molecule right here, but we will also end up with carbon dioxide in this case. What are some other transformations that we looked at? If we take this triple bond and we want to make, if we want to
I'm sorry, I have a question.
Go for it.
Isn't there also a different case when the triple bond is an internal compared when you do that splitting?
Yeah. So if you have a terminal alkyne, right? If you have this, a terminal alkyne, when you treat this with ozone in the first step, followed by water, and that's what this is. This is a terminal alkyne because we have a proton here. When you do that, you end up with the carboxylic acid, right? That came from this R over here, okay, or that side of the molecule, if you will. Okay, just let me tidy this up here. There we go. So you end up with a carboxylic acid, but from this carbon right here, you end up making carbon dioxide. When you have an internal alkyne like this, you do the exact same thing, okay? Ozone followed by water. Now you end up with 2 carboxylic acids. So it's only when you have a terminal alkyne that you end up with carbon dioxide. Does that help?
Yeah, I just wanted to double check because I thought there was 2.
All right, there we go. So again, terminal alkyne, you end up producing CO2. When you have an internal alkyne, you end up with 2 different carboxylic acids. Well, if these 2 R groups are identical, then you end up with the same carboxylic acid. All right, there we have it. Well, how do we take that terminal alkyne and how do we just add 4 bromines to it? To do that, we're just going to treat it with excess bromine. If you only want to add 1 equivalent of bromine to produce the alkene like this, okay, here we go, like that. In that case, you would just use bromine, but I would be sure to write 1 equivalent because you only need 1 molecule of it. What else? We've looked at the anti-Markovnikov addition of water across the triple bond to make an aldehyde. Right, these are conditions that you have to be aware of. You can use 9-BBN or you can write R2BH, right, just to show that it's a hindered borane in the first step. And then in the second step, you use hydrogen peroxide and sodium hydroxide. That works. If you want to make the methyl ketone, we've looked at that today. Oops, can pretty that up. There we go. To make the methyl ketone, you use mercuric sulfate, HDSO4, sulfuric acid, and water, like that. Anyhow, that's quite a bit of chemistry there. And of course, we could take that internal alkyne, right? We can reduce that internal alkyne to a transalkene, right? If we want to make this guy, or we can reduce it to a cis-alkene. We want to make this, right? The cis-alkene is going to be done with hydrogen and Lindlaier's catalyst. And then the trans reduction is done with sodium metal in liquid ammonia. All right, and then if you just blow the whole heck out of it, just using hydrogen, and let's use nickel as a catalyst. You got it from a margarine factory. 1, 2, 3, like that. There we go. You'd end up with propyl cyclohexane. All right, that's a pretty good review of all the different reactions that you have to know. So again, whatever your strategy is going to be to memorize those, whatever it is, it's got to work, right? You got to come up with something that works for you, and everybody's a little bit different. All right, let's try taking a look at some more synthesis problems here. The idea is to do them until you can't stand them anymore, right? Then what do? You take a 5-minute break and you get back in the game. So this is question 11.18, and I think that this is a really good problem. Let's see, let me fix this up. Like that. If we have this alkene, so this is what, 3-methyl-1-butene. We take this and we want to make this carboxylic acid. We start out with a total of 5 carbons in our starting material, but we only have 4 carbons in our final product. So how do we lessen the number of carbons in the carbon skeleton? Again, we don't have many ways to do that, and we also don't have many ways to make a carboxylic acid. So you should be pretty quick, and I don't like to talk about the velocity with which you do problems, but you have to have some speed, and you have to be able to figure out, well, if I was to start with this alkyne, all I'd have to do is take this and treat it with ozone, followed by water, and I would make the desired carboxylic acid. That greatly simplifies the problem. When you can solve the first step of retrosynthesis, it can just, decrease the complexity of the problem very quickly. So if we want to take that alkene and convert it to that terminal alkyne, what are we going to do? The first thing is we're going to brominate that with Br2. No light. This is not a radical bromination. This is just a bromination in a solvent like dichloromethane. And when we do the bromination, we end up with the vicinal dibromide. So we're going to have a bromine here, and we're going to have another bromine here. In order to produce that triple bond, the first step, we treat it with excess sodium amide to do the double elimination and the deprotonation. And then in the second step, we put water on it. That will give us the terminal alkyne. And then in the last steps, you treat it with ozone followed by water. So not only will you end up with this product, but you'll also end up making CO2 gas, right? Which is just going to go up the smokestack. Will go up into the atmosphere. You're not going to collect that. Okay, let's try another one where we have a change in the carbon skeleton. What if we have a primary alkyl bromide like this, and we want to make this carboxylic acid? This is a good one too. I want to make this carboxylic acid. Look, at this point, you should be thinking, really, I've only got one option to make a carboxylic acid, right? You've only got one option. In organic chemistry 2, you learn Avogadro's number of ways of making carboxylic acids. It's probably the longest chapter you ever do in organic chemistry is the carboxylic acids chapter. Very long chapter, piles and piles of reactions, more than double the reactions that we see in one chapter in this class. The only option that you would have is to have this guy, right? To have that molecule, to have that terminal alkyne, and to treat that with ozone followed by water, right? Because you're going to clip it there, so you're going to end up with a product plus CO2 gas, but that's neither here nor there. Again, that greatly simplifies the problem. We want to go from here to here, right? Again, something that I didn't address is that there is a change in the carbon skeleton. These are things you should take a look at from the get-go. Here we have a total of 4 carbons. Here we have 1, 2, 3, 4, 5 carbons. Right, so if we're only adding 1 carbon, we have no way of adding 1 carbon. But to go from here to here, you're adding 2 carbons. And we do have ways to add 2 carbons, right? what if I take this primary alkyl halide and I treat it with sodium acetylide? Right? Then I'm just going to do an SN2 reaction, and I'm going to end up producing that terminal alkyne that I wanted from the get-go. So we're going to have something that looks like this. There we go. Now the question becomes greatly simplified. Now we're just going to treat it with ozone, followed by water, like that. This is the kind of problem that it's only 3 steps, but you really have to know your stuff, in my opinion, to figure this one out. It's kind of tricky because you're starting with 4 carbons, you only end up with 1 extra carbon in the molecule. You know, you really have to be able to remember that in order to make the carboxylic acid, you have to start with the terminal alkyne. All right, well, that's all I had planned for today.